Okay, first of all, I would like to say thank you to the people of TCCIP and NCDR for inviting me to this workshop and allowing me a chance to give a talk here. Okay, so the title of my talk today is Projection and Uncertainty in CMIP5. So the projection would be useful or wasteful in comparison with the uncertainty. Okay. So I would like to start with a very brief summary of IPCC report published from 1990 to 2013. So the messages from these IPCC report can be summarized very simple way. One thing is that we have I would use this screen here. One thing is that we don't have global warming signals. And then the second thing is that this signal might be caused by man-made activity. This may be the most brief summary of the IPCC report. But when we take a look at the signal, for example, the global temperature increase, then this signal always comes with the certain range, which we call uncertainty. If you look at the right figures, this figure shows the projected temperature change from 2000 to 2100. Projected by RCP 8.5, which is shown in red here, and projected by RCP 4.5, which is shown in blue here. Then you can see that the average temperature increase is about 1.8 degrees Celsius, but it comes with the uncertainty shown here, which is about 1.3 from the bottom to the top. And then if you look at the temperature change from RCP 4.8.5, then the temperature change will be about 3.7 with the uncertainty ranging from 2.6 to 4.8, which is a bit bigger than RCP 4.5. And then this uncertainty you can also see even in the observations. So the left panel shows the observed global temperature change, which is about 0.85. But depending on the data you use, you can get some slightly different global temperature change, which is about 0.65 to 1.06. And then another example would be the sea level rise. We know that sea level would rise in the future. And then the right panel again shows the projection from the CMIP5 model simulations. And then if we consider the RCP 8.5, the sea level rise would be 63 centimeters, with the which varies from 45 to 82. And then if you look at the RCP 4.8, this would be about 47 on average, but it can vary from 32 to 63. And again, the uncertainty range is a bit greater in RCP 8.5 than in RCP 4.5. And you can also see some historical sea level rise from the gauge data, and then you can also see some uncertainty even in the observation data set. And maybe the next important example would be the extreme rainfall. a myriad of papers actually indicate that there must be more frequent extreme rainfall as time goes on, and then these scientific evidence always comes with some certain range in terms of probability. So the IPCC report says that we have signal as well as uncertainty, and sometimes uncertainty raises the doubt about the credibility of the signal, and sometimes it even devalues the credibility of the signal. And in addition, if we want to use these model simulation for practical use, for example, if we want to use this data in downscaling or process modeling, then maybe this uncertainty would be enhanced. So this is one example taken from the facing the fractions dilemma given by Dr. Kaspar Ammann when he had downscaling workshop in APEC Climate Center. He gave a nice example shown in this figure. So here is the present, and then this small column shows the variability recorded at the present. And then some people in Denver Water Bureau, they did some regional downscaling using various GCM simulations, and then they found out that temperature would increase within this circle in the x direction. And then in terms of precipitation, some model shows the increased precipitation plus here, so some model, the downscaling result shows the increased precipitation in the future, but on the other hand, some other model shows the decreased precipitation, even though they get the result. Of course, this result comes from the various models, but they use the same scenarios, for example, ISP 4.5, 8.5, and then the uncertainty grows up when time goes on. So we know that there is uncertainty depending on scenario, and this uncertainty tends to grow up as time goes on. And then if we use, for example, regional downscaling, this uncertainty may be even worse, it becomes even worse. And then if we go down further, then, for example, if we use the watershed scale hydrology modeling, then this uncertainty even becomes worse. So if we want to give this data to practitioners, then they would say that maybe I'm not going to use this data because it has a lot of uncertainty, and then I have to deal with a lot of data sets. So why should I use this? And then as a climate scientist, this might be pretty much frustrating, because I want to give them data with some relevant level of credibility. So, but we cannot give up here, so we have to face and then challenge it together. So what we want emphasize here is that at least we can tell them which data to use, or just the best, and then what characteristics of the climate data is of interest. So I want to say something about how can we reduce uncertainty without loss of generality, in other words, signal, and then how can we extract signal that beats the uncertainty by using best model approach. So the first target we were interested was cloud feedback processes. So because the cloud feedback process is very notorious for the very large intermodal spread. So we take this process to select the best model among the CMIP5 simulations. And then in order to select the best model, we have to have some metrics to evaluate the performance of the models. And then in order to do that, we have to know some observational evidence which shows correlability between some meteorological variables with cloud feedback processes. So we investigate some theories, and then we found out that if SST increased, then the low troposphere destabilized, I mean the stratification becomes unstable relatively, then this makes this causes more convection. Therefore, the stratiform cloud tend to convert into cumuliform clouds, and then because of this enhanced deep convection, we have more chance to have high cloud, which is a form of cloud ambient. And another variable must be large-scale circulation, which may be represented by the subsidence or open motion. So when we try to evaluate the CMIP5 models, we decide to take a look at some key variables, such as cloud amount itself, including total cloud amount and low cloud amount and high cloud amount, and SST, and stability, and cerebral pressure, which is proxy for the subsidence, and also the long wave cloud radiative forcing, short wave cloud radiative forcing, and the sum of the long wave and short wave cloud radiative forcing, which is shown here, CRF. Okay, so before we select the best model, we take a look at how uncertain in these cloud feedback processes in the CMIP5 simulations. So if you look at the red line here, this is the ensemble mean of the total CMIP5 simulations used in this study. We have used 32 models to get these figures. And then the pink shading shows the intermodal spread. Then if you look at the ensemble mean red line here, then the total cloud would be decreased as time also, as time goes on. But some model says the cloud amount will be increased in the future here. But most of the models indicate that the cloud in the future will be decreased here. Anyway, okay, then what about the cloud radiative forcing? Here again, the red line indicates ensemble mean region, and then it shows that it is relatively neutral during the present century and slightly goes up in the next century. Then what about the model spread? There is some ranging among the models. So some model says that the cloud radiative forcing would be negative in the future here, but others says no, it's not. It's going to be positive, shown here. But if you think about the overall cloud radiative forcing, I mean the short wave radiative forcing is usually negative because it reflects the solar radiation. But when we think about the long wave radiative forcing, it might warm the planet because it absorbs the long wave radiation from those and then lead it to the surface and to the space. But if you sum these two cloud radiative forcing, the overall effect would be slightly negative, which is shown which is revealed by the previous study. Then why in the future we have the positive cloud radiative forcing in terms of mean sense? Because total cloud is decreasing here. Okay, so this is quite consistent to each other. Okay, then the last one is C-sub temperature. Oh, sorry, the model used in this simulation is this ensemble map is 21. Okay. And then C-sub temperature, of course, this will be increased. And then we see that most of the models, actually all of the models, indicate the increase of the C-sub temperature, which is quite different from the total cloud amount projection and cloud radiative forcing projection. Okay, then how to select best models? Because we know that total cloud amount have some covariability between some meteorological variables such as SST, sterility, and then stereo pressure. We take a look at how these covariability looks like in the model simulation, and we calculate the pattern correlation map between the observation and model. All of these correlation map between the TCA and other variables, and this is the result here for the four major low-level cloud regions, which is Peruvian, Namibian, and Californian, and Equatorial Eastern Atlantic. And this is quite complicated figures, but and this shows the correlation between the TCA, SST, LTS, and cerebral pressure. And we do another analysis to select best models, which is the PCC versus normalized root mean square error scatter diagram, which is shown here and here. On the left panel shows the climatology between the high cloud amount for the high cloud amount, and y-axis shows the normalized root mean square error, and x-axis shows the pattern correlation. And then this one is for the low cloud, and the top figure shows the total cloud. And then the right panel, light column here shows the long wave cloud radiative forcing, and the middle one is the short wave cloud radiative forcing, and then top is for the total cloud radiative forcing. And then the right panel shows the same figures, except that we use the climatological annual cycles. So based on these and then the figures shown previously, this one, we select three models, three best models. And then the result for the cloud radiative forcing is appeared here. So the first one is XS 1-0, and the second one is Hedgen to CC, and the third one is Hedgen to ES. And then the black bar shows the long wave radiative forcing, and then the hatch bar shows the short wave cloud radiative forcing, and then the gray one is total cloud radiative forcing, and this one is for the total cloud amount. And please note that XS do not provide the low cloud amount, therefore this value is not zero, this value is just not available. And then if you look at the sign and magnitude of all these variables among these three models, they are pretty much consistent to each other. So negative long wave radiative forcing here from the XS, and Hedgen here, and also Hedgen to ES here. And then short wave radiative forcing, positive, and the magnitude also pretty much similar to each other. So based on the selection of these best three models, we calculate again the total cloud amount from these three best models, which is shown in blue line here, the mean of these three models. And then if you compare this blue line with red line, which is the ensemble mean of the total models, they just goes together as time goes on. I mean, the red line varies like this, as well as the blue line varies pretty much similar with the red line. And then if you look at the blue shading, which is the uncertainty obtained from these three models, the uncertainty range is pretty much reduced when compared to the uncertainty range from the 21 CMIP5 models, which is shown in pink here. Therefore, this figure indicates that if we select these three best models, then we can get average signal, which is pretty much similar to the total ensemble mean, but we can also get very reduced uncertainty by using these three best models. This is for the total cloud amount, and this is for the cloud radiative forcing. So, as I mentioned before, cloud radiative forcing should be negative and should follow to the pattern of the total cloud amount. So, total cloud amount is going slightly down in the future. Therefore, the cloud radiative forcing going slightly up in the future due to the reduction of the cloud amount. Okay, and then this is the SST. Okay, the next example for the use of the best model approach is for the weather variability. We also apply this concept to the daily variables, whether this best model concept is valid for the very short timescale variability. So we use the interdiurnal variability, which is defined as the magnitude of the difference in the daily variable between two consecutive days. So this is just simply the difference between daily variables from one day to next day. And then we take the absolute value, and then we can calculate how this absolute value can change as time goes on. And then if we average this interdiurnal variability on a particular month, then we can get some mean behavior of this interdiurnal variability. So what does this mean? So if we have reduced MIDV, mean interdiurnal variability, that means the synoptic system would be weakened, and vice versa. And if we have the increased MIDV, then the synoptic system will be stronger. So this is the meaning of these two these indices. And then we select three best models for the maximum temperature, minimum temperature, and wind speed at 10 meters and precipitations. And then we test the signal of these three best models to the noise, which is obtained from the standard deviation of the total models, total CMIP5 models. And then in this analysis, we only use the 15 CMIP5 models because only 15 models provide daily data for some particular time in next century, which is the 2030 to 2056, 27-year period, and another one is the 2073 to 2099, another 26 years. So we take a look at whether the best model result can beat the intermodal spread. Then we found out that the blue means the reduced interdiurnal variability, and the dot shows the area where the signal is significant. Then we can find out that in January, mostly, the temperature change is most significant. And then also we found out that wind will be changed significantly during the April. So the conclusion is that the result from the best model approach suggests a reduction of uncertainty without loss of signal, and it also allows us to detect the signal against intermodal spread. And then this method seems to be applicable to high frequency variability. Therefore, it might be a potentially smarter way to use the best models identified with well-designed matrices for processes and feedbacks of interest. That's all. Thank you.
Thank you. Any question?
Thank you so much. I think very important talk. I hope it's okay to take some pictures. Just two quick, maybe points of clarification. Did you include mean sea level pressure in your analysis of variations in weather systems?
In weather systems?
Yes.
No, because we are mostly interested in temperature change because it is most, useful. We thought that it's most useful information to the public, so we just choose the temperature and precipitation and wind.
Okay. And the other one was, there's one slide where you show results from access and hedging 1 and hedging 2, I think, or 3. My question is, aren't they almost the same? Hedging 2. The access, I believe, the atmospheric component is imported from hedging, so we end up with the same models. So you would expect those three to be very similar, or is that taken into account?
Okay, maybe I don't know about that. I don't know well about how the model component looks like to each other. So maybe I cannot answer your question.
Any other question?
It's very interesting to probably compare the three test models that have similar content, as Roger just mentioned, because it seems that you find three similar models, and therefore their variability will be smaller. And the idea of using multi-model is that we assume that the performance of each individual models are the same. So we output of different models constitute a random sample, and they are equally weighted. But in fact, the performance may be different. So if you consider similar models, of course their uncertainties will be reduced. So I think that probably the next step to investigate how many clusters within your total models is used.
Yes, very good point. Yeah, that comment will be taken very seriously to us, and then yes, the similarity between the models, the point we cannot catch yet, but we have to take a look at how the model component is similar between the model, CMIP5 models. Thank you for coming.
Any other question? If not, we move to next talk.